We're going to continue our discussion looking at something called the electron configuration. The orbital diagram is shown on the right here. On the left, we have the symbol. In the middle, we have the electron configuration as written according to the abbreviations that are appropriate. And on the right, we have the orbital diagram, which shows a single electron in the 1s suborbital. This is a similar outline for helium. You'll recall that I said that helium has 2 electrons. The helium symbol from the periodic table is He. Principal number was 1. The second, or L, or angular quantum number was 0, so it's S. And there are 2 electrons there, so that's 1s2. And then the orbital diagram shows 2 electrons with opposite spins. So these 2 electrons would have the same quantum numbers, except one would have a spin number of plus 1/2, the other would be minus 1/2. So that the Pauli's exclusion principle would still be taken into account. This is the next one. This is lithium. Lithium has 3 electrons. Once you get to 3 electrons, you have to move up an energy level. And so you have the 2 electrons. So first of all, you have the symbol Li on the left. In the middle, you have 2 electrons at the 1s level. So 2 electrons that have n equals 1 and L equals 0. The next electron, n equals 2 and L equals 0. And this shows the orbital diagram showing that that next electron is separated from the other 2 that are paired. And then here is the next element in that series. This is beryllium. It has 4 electrons, and everything is the same except now you have another electron with the opposite spin that's in the s suborbital, but at the 2 energy level. The 2 electrons that are in the 2s level only differ in the fact that their spin numbers are different. This is the next one, and what this shows is how to diagram or do an orbital diagram for the p level, which is when L is equal to 1. And so you have the configuration that looks like beryllium, and then you've added 3 spots because a total of 6 electrons can go into this area, and the first one drops into the first level. Carbon does the same thing, but now has an additional electron and the electrons spread on each orbital axis first, and then they pair up. So instead of having 2 together at one orbital axis, you move out from one orbital axis to the next orbital axis. And here are some subsequent examples that show how the remainder of the 2p level fills out. You have 2p, you have 3 that spread out across the 3 orbital axes in the 2p level, and then they begin to pair up with oxygen, fluorine, and then finally neon. And with neon, you have a totally full 2p suborbit. The outermost electrons in any particular electron configuration is called the valence electrons. These valence electrons are going to become very important because they are responsible for the interactions of atoms with other atoms and the bonding that subsequently occurs. The electrons that are inside the valence electrons are called the core electrons. The core electrons can be abbreviated to simplify when you have a very long string of, say, an element that has, say, 71 electrons. You don't want to write all of this 1s2, 2s2, 2p6, blah, 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 blah. And so it's common to abbreviate the core and then only write the valence electron. And the abbreviation for the core is the closest noble gas symbol. So for example, sodium has 11 electrons, so it's the next element after neon. It has a single valence electron in the 3s suborbit. And the way to abbreviate that is to write the symbol neon, representing the core electrons, and follow that with the valence electron. Now, when we do this for a quiz or test, early on, I'm going to want you to write things out to show that you know what you're doing. But once I'm confident that you know what you're doing, then I will let you use the abbreviated method. This periodic table basically shows the outermost shell electron configuration for each element. So for example, if you look at potassium, which is 4, period 4 in group 1, you see that the outermost electron is 4s1. If you look at copper, it's also period 4, but now it's in the transition. You see that its outermost is 4s1 and 3d10, and so forth. And you can see that various ways to look. You could abbreviate, say, RB, which is 5 in group 1. You could abbreviate that KR for krypton, then 5s1. If you go down a group, you'll notice that as you go down a group, the outermost electrons are very similar, except for differences in principal quantum numbers. So if you go down group 2, for example, beryllium's 2s2, magnesium's 3s2, calcium is 4s2, SR is 5s2, barium is 6s2, radium is 7s2. If you go over here to 17, the top one is fluorine. It's 2s2, 2p5. The next one, chlorine, is 3s2, 3p5. Bromine is 4s2, 3d10, 4d5. Notice if you drop the 4d10, it's exactly the same as the one above, except for the number, and so forth. And this is one of the reasons why elements in the same group tend to have similar chemical properties. So why don't you get out a piece of paper, and you can stop the video and write the electron configuration and the orbital diagram for phosphorus. Stop the video now and do it. The symbol for phosphorus is P. The configuration is 1s2, 2s2, 2p6, 3s2, 3p3. You could have written that Ne for neon, then 3s2, 3p3. The orbital diagram is shown here as well, and you'll notice that at the 3p level, you have one electron in each axis before you pair up an electron. Let's try oxygen. Oxygen has 8 electrons. Stop the video now and give it a try. This is oxygen. Oxygen has 1s2, 2s2, 2p4. People generally don't abbreviate that HE. They just write this out because it's short enough as it is. And here's the orbital diagram, and you'll notice that the 4th p electron has paired up, and the other 2 are out there on their own. It would be incorrect to write 2 pairs in 2 boxes and have an empty box out on the 2p side. Now stop the video and try these 3. Remember that when you have a positive cation, you lose 1 electron. If you have a negative anion, you gain 1 electron. If you have a positive 2, then you've lost 2 electrons. So give this a try and let's see what this looks like. This is the first one. sodium plus, and notice it has the same electron configuration as neon. This is chlorine minus, and notice it has the same electron configuration as the noble gas next door. And this is iron, and it does not have a noble gas configuration, which is sort of interesting, but this is what it looks like when it loses its two outer electrons.